Now, in addition to building a distribution curve like we did in the last problem, we can use normal CDF to answer some of these questions too. So in this particular problem, we're going to suppose that about 13% of the population is left-handed. A 200-seat school auditorium has been built with 15 lefty seats. I don't know if you've ever sat with one of these, but the little mini desk is on the left instead of being on the right. In a class of 90 students, what's the probability that there's not enough seats for the left-handed students? Okay, this is useful. I know that P, now remember that's the parameter for the whole population, is going to be 13%. So P equals 0.13 because they tell us in the problem here that 13% of the population is left-handed. Normally we don't have that information, but in this case we do. Okay, so P is 0.13. And then P hat, that's the proportion of left-handed students in this class of 90. Okay, so that's the sample proportion. And I don't know how many students are lefty out of those 90, but if I did, the number of lefties divided by 90, I would get my sample proportion P hat. Now, before I do anything with a normal model with a normal model distribution, I have to check my conditions. Okay, so remember, my first condition is that this sample has to be random and independent. I'm going to guess that this one's true. They didn't really tell us. If the class was something specifically for left-handed students, or if the college had a club for left-handed students and they all signed up for this class together, that wouldn't be a very random sample. But generally, I think that the people who enroll in a class, they don't do so based on whether they're right or left-handed. So they don't tell us that we have randomness or independent here, but I'm going to assume that we're okay. The second condition is that our sample has to be big enough to have 10 successes and 10 failures. To test that, I'm going to do n times p. N times p is, in this case, 90 times 0.13. When I do 90 times 0.13, I get 12, which is bigger than or equal to 10. Okay, so I've got my 10 successes. For failures, I'm going to do n times 1 minus p, which is 90 times 0.87, which is 78, which is also bigger than or equal to 10. So I've got my 10 failures. The last condition I need is that my minimum population needs to be bigger than or equal to 10 times the sample size. So in this case, that means my population has to be bigger than or equal to 10 times 90. It's got to be bigger than or equal to 900. Now they tell us, or they don't tell us how many students go to the school, but colleges generally have thousands and thousands and thousands of students. So I think we can say that this one's met also because college campuses have lots and lots of students. Okay, so because we've met these three conditions, we can use a normal model here. Now, we're not always going to draw this, but I think it's really helpful at the beginning to draw our normal distribution curve to think about what's going on. So here's my normal curve. And right in the middle, how many left-handed students do I think are going to show up in this class? I'm guessing it's going to be 13%. I'm guessing it's going to match the general population. So remember, that's from the central limit theorem, that the average of our sample or the proportion for our sample should match the proportion overall. Now, I also want to do the +1, +2, +3 standard deviations on either side. And to do that, I need to calculate my standard error. So standard error here is going to be the square root of 0.13 times 1 minus 0.13, which is 0.87, divided by 90. And when I do that, I'm going to round a little bit just to make my life easier. You might want to keep more decimals, but I'm going to round a little bit. I'm going to call this 0.035. Okay, so when I make the rest of this curve, I'm going to go out 1, 2, 3 standard deviations in the positive direction, 1, 2, 3 standard deviations in the negative direction. I get 0.165 here, 0.2, and then 0.235. So those are the positive direction labels. And then in the negative direction, I get 0.095. 0.06, and 0.025. So if I'm the teacher of this class, I'm kind of expecting there to be anywhere between 0.25% lefties in my class and 23.5% lefties in my class. So it's going to be somewhere between maybe 1 or 0 all the way up to, close to a quarter of my students are lefties. And all of those are reasonable. Now, where do I get in trouble here? Right? Remember, this is about will all the lefty students have a lefty desk? So if I have 15 lefty students, I'm actually okay. I think lefty we do with a Y. Lefty, let's try this again. Lefty students. If I have 15 lefty students, I'm fine. They all have a desk, no problem. I get into trouble when I have 16 or more left-handed students. Okay, at that point, I'm in trouble. I'm in trouble. Okay, and so that's the number of lefty students. Let's turn that into a p hat. So what p hat gets me in trouble? That's going to be 16 over 90. Which I can rewrite as a decimal. That's about 0.18. Okay. If we go back up to our distribution curve, I can think about where 0.18 is. It's kind of maybe here-ish. Okay. So all of this part of the distribution, that's where I don't have enough lefty desks. Okay. So this green area in here, this is all the ways that I cannot have enough lefty desks. Now, this question wanted me to find the probability of that happening. What's the probability that I don't have enough seats for my left-handed students? But I know from our section on normal model probability from last week that that's the area of this region I just shaded. And I can find that area by using normal CDF. So the probability that I have not enough, oh, if I can spell, not enough lefty desks, I can calculate that with normal CDF. Okay, remember, normal CDF takes 4 pieces of information. It takes the smallest number I'm interested in, the biggest number I'm interested in, the mean, and the standard deviation. So I know that the mean is 0.13, right? That's the middle of my distribution. And I know that the standard deviation is 0.035 because in this case, we're talking about standard error. I also calculated that the p hat where I get in trouble is 0.18. So that's the smallest number I can have where I'm in trouble. 0.18, I'm in trouble. But anything bigger than that, I'm in trouble. So we could put a huge number here, like 100 or 1,000, but really you can't have more than 100%. So even 1 will give you an accurate answer. And when I put that into my calculator and have it calculate normal CDF, I get 0.08 or 8%. So there's actually an 8% chance that I don't have enough lefty desks.